Hey there everybody. In this first video for trigonometry, we're just going to hopefully quickly go through some of the topics that we worked on in the first week that you've maybe forgotten or have slipped out of your mind over time. So let this video be a bit of a recap of what we worked on from that first week. Okay, let's get started. So the things we're going to go over in this video are as follows. And this is not a comprehensive list. This is just sort of what I was thinking about when I was imagining you guys trying to go back and remember. So things from the first week of the trimester that I think I maybe forgot. We're going to talk about evaluating trigonometric ratios of special angles. Think your 30 degrees, your 45 degrees, your 60 degrees. We'll use right triangle trigonometry to solve a couple of problems. And then we'll make sure that we can express angles in both degrees and radians. Starting with evaluating trigonometric ratios of special angles, I'll remind you of your two special triangles. You should have those in your notes still already, so make sure that you are reviewing those things there. The first we talked about, I believe this was the first one, was the 30, 60, 90 triangle. And knowing how those sides are labeled, the ratio of those sides is going to help you remember those special angles and their trigonometric ratios. Across from the 30-degree angle is a side that has a length of 1. Across from the 90-degree angle is a side that's twice as big, 2. And across from the 60-degree angle is a side that is somewhere in between. It's the square root of 3. So use that to go back and review things like the sine of 30. Opposite leg is 1. Hypotenuse length is 2. So the sine of 30 degrees is 1/2. Or the tangent of 60 degrees. 60-degree angle, the opposite leg is the square root of 3. The adjacent leg is 1, so our tangent of 60 degrees is the square root of 3. Likewise for our 45, 45, 90 right triangle, where both angles that are acute are congruent to each other, which means that each leg will also be congruent. We labeled those with a 1, so the length of the hypotenuse worked out as the square root of 2. That way, when I need to know something like the sine of a 45-degree angle, regardless of which 45-degree angle, the opposite leg has a length of 1, the hypotenuse has a length of 2, and making sure that we rationalize our denominators whenever the situation arises. So make sure that these are, values that you have in your mind that you go back and remind yourself of. Okay? Moving on, the next thing we talked about was using right triangle trigonometry to solve problems. Namely, we use those to solve missing parts of right triangles. I'm not going to solve the entire right triangle here. We'll just solve for some of the parts. For example, if I wanted to find the length of this side labeled x, that side is opposite this given 38-degree angle, and this length of 18 is the adjacent leg. Since I know the adjacent leg and I need the opposite leg, I'm going to use a tangent ratio to set up an equation to solve for my missing part. In this triangle, the tangent of our 38-degree angle is opposite leg x over adjacent leg 18. We will solve for x by multiplying both sides by 18. And x can be found by taking 18 times the tangent of 38 degrees. We'll come up with some more information about calculators if you don't have one. A graphing calculator is very helpful, but we'll have some other tools coming up soon. Make sure your graphing calculator is in degree mode, not radian mode. So I can take from my calculator 18 times the tangent of 38 degrees to find the length of that side x. It is about 14.0631. To do one where we maybe need to find a different leg, there's my 72-degree angle. The leg that I need is the opposite leg, and I'm giving the hypotenuse. Well, I guess I'm missing the opposite on both of these. So since opposite is needed and hypotenuse is given, I would be using a sine ratio. Remember your good old SOHCAHTOA to help you get your ratios straightened out. The sine of that 72-degree angle is the opposite leg x over the hypotenuse 16. Multiply both sides by that 16 to solve. Remember as well, on some of these you would need to find that missing angle. That missing angle could be found here because all the angles inside this triangle have a sum of 180 degrees, and we already know the two of them. So we can solve for that missing angle, but let's finish up finding that leg. 16 times the sine of 72 works out to be approximately 15.2169. But if I did need to find that missing angle, we could take the two angles that we know and subtract them from 180 to find that missing angle. The other situation where you might need to solve for some missing parts is if we are given two sides but need to find a missing angle. Let's say, for instance, I needed to find the measure of angle A right here. Based on the lengths that I am given, I'm provided with the side that is opposite angle A and the hypotenuse of this right triangle. Well, as we saw before, opposite and hypotenuse remind us of that sine ratio. So in this figure, the sine of angle A is equal to 15 over 55. We could then find the measure of angle A by taking the inverse sine of 15/55. And we reasoned that out before we dismissed from class for a while, I suppose, by thinking of that inverse sine as a literal inverse operation. Like the opposite of adding is subtracting, or the opposite of multiplying is dividing. The opposite of the sine is the inverse sine. So those terms can almost cancel each other out, and I can take the inverse sine of that ratio, and my calculator will provide me with the angle measure that has that ratio. That's a better spot for that calculator. It's about a 15.8266 degree angle. And the last thing to remind you of, in terms of things that you maybe forgot, is working with angle measures in both degrees and radians. So first I'll remind you that radian measure is the distance traveled around the unit circle. And the unit circle is that circle whose radius is 1 unit in length. Think of the distance traveled around that unit circle as a part of the circumference of a circle whose radius is 1. Since that circle whose radius is 1 has a circumference of 2 pi, that means an angle that measures 360 degrees is equivalent to an angle that measures 2 pi radians. Because if a point travels all the way around the unit circle's circumference, it has traveled a full 2 pi in distance. That allowed us to find some parts of that circle's circumference and give us some radian measurements that represented a portion of that 360. 180 degrees is half of the circle's circumference, 1 pi instead of 2 pi. 90 degrees is a fourth of that circle's circumference, pi over 2. And 270 degrees is 3/4 of this circle's circumference, which works out to be 1.5 pi, which we wrote as 3 pi over 2. Between pi and 2 pi is 3 pi over 2. Before we left, we did also talk about the other angles here and their radian equivalencies. We might throw another video up here to remind you how those things are calculated. But for now, go back and review your unit circle, which you hopefully brought home with you. Otherwise, I can throw a link out there as to where you can find one and download it on your own and fill in those spots. So the last thing we'll talk about is just a little bit of converting. We did that right before we left as well. Expressing angles in either one of those two forms of measurement, radians or degrees, can be done by finding a conversion factor. Just as there are 12 inches for every 1 foot, and you could use that to convert between those two units, there are 180 degrees in every 1 pi radians. So I can use that as a conversion factor to convert back and forth between these two units of measurement. So if I want to convert from 40 degrees into radians, I can take that 40-degree angle and multiply it by the conversion factor that will change my units from degrees into radians. So I'm going to multiply by pi radians over 180 degrees so that my units of degrees will cancel each other out. Think of this as multiplying to change from feet to inches or inches to feet, but changing from degrees to radians. That would give us 40 pi over 180. We will leave our radian measurements in terms of pi, but reduce our fractions to lowest form. dividing both top and bottom by 10, and then ending up with 2 pi over 9. Now this is a little embarrassing, and I've already come this far in the video, so I'm not going back and changing it. But I didn't realize when I created these two questions, I actually had the exact same measurement both times. So let's change this 2 pi over 9 into something else, because we just learned that 2 pi over 9 is already 40 degrees. Let's change it to something so we can actually do a conversion for real. So let's just change it to 3 pi over 10. Seems reasonable enough. To convert that from radians to degrees, we again use this conversion factor here. There's pi radians for every 180 degrees. So we'll multiply that by a conversion factor that will remove the unit of radians and apply the unit of degrees. Now, one thing to take note, the pi here that's going to cancel is not a label that's canceling. This is 3 pi over 10 radians, and it's that unit of radians that is canceling and converting to degrees. We just happen to get a little bonus cancellation between those pi's. Pi divided by pi reduces to 1 and divides away. Then we can multiply and simplify. Need to use your calculator to do this, go right ahead. 3 times 180 would be 540 divided by 10, and that's a 54-degree angle. Just for the sake of safety, since I already made one error recreating the same number twice, there we go. So there are 3 topics right there from the first few days of class. If you have more questions, please make sure you contact me. More information will be coming, but until then, take care.